Good morning. So our topic for the day is force coupled system, and I am E. Ilavenil, Assistant Professor, Department of Mechanical Engineering, Thandai Periyar Government Institute of Technology, Vellore. So a force coupled system. The effect of a force acting on a body is the tendency to push or pull the body in the direction of force and to rotate the body about any fixed axis which does not intersect the line of the force. So this is something that we halfway already discussed. Of course, fully we have already discussed in another lecture, but not in this particular fashion. So we have seen that a force is capable of push and pull. We have also studied that a force is capable of rotating a body. Okay, so when it rotates, whenever the force is at some offset, which means it does not intersect with the center of gravity of the body. Okay, so when the force is acting at the center of gravity, it is going to be a pure translatory effect. So whenever a force is acting at some point which may not be the center of gravity, although as we say that there is a tendency for rotation, the force also has a capacity to move the body linearly along its direction. So a force is capable of the so-called dual effect of translation and rotation. The dual effect is brought easily by replacing the given force by an equal parallel force and a couple to compensate for the change in the moment of the force. So here we have quite a few figures. The figures are going to demonstrate how the first part given in the figure is an equivalent of the second part, which is again equivalent of the third part. So in the left extreme, a body or a system, as it can technically be referred, is at the left extreme with a single force through some procedure is converted into a force and a couple as shown in the third one through a procedure shown in the second one, or that the middle one. Okay, so here force F acting at point A, as you can see in the figure. So here you have point A at which there is an arrow mark which is the representation for the force acting upon. So a force is acting upon in the direction as shown there with the magnitude F at point A. Okay, and here with the figure shown in A, which is also available in the middle portion of the figure, at point A there is a force available. So here we are adding one more force at B in both the directions with same magnitude F and F. So with the two forces which are acting at the directly opposite directions with same magnitude means that as a net result we have not added anything in excess. So there is point A where there is a force, and at point B we have added two equal and opposite forces at the same point, which means that we have not added anything at all. It is an equivalent of not adding anything. So we have added two forces actually which cancel out each other. But for our purpose we are not going to cancel them, not for that we have added it. So we are going to combine the force at A moving towards the right and the force at B moving towards the left, separated by a distance small d. They will constitute a couple. Okay, we can call it a couple or a moment. Of course, two equal and opposite forces separated by a distance can be called as a couple. In fact, it has to be referred as moment due to a couple, but still the word couple should be sufficient. Along with that, the right side force is also available. So the single force, which is equal to the three forces as mentioned in the middle figure, is also equal to the single force at B along with a moment or a couple whose magnitude is Fd. Okay, so this is what the figure indicates, and that is how at different problems, as we move a force, there is an additional couple involved, or say any single force can be resolved into a force and a couple, or the vice versa, where a force and a couple can be represented as a single force when it is placed at the appropriate position. So when you place that at the appropriate position, you call that as a resultant. Okay, you call that as the resultant force acting at the appropriate point in the rigid body where it is represented as a single force without any moment. Okay, this can be extended for several forces and several moments together. Of course, when there are several moments together, we add up all the moments, of course vectorially, and represent that as a single moment, and we add all the forces vectorially and represent that as a single force. And again, with that resultant moment we already obtained, we also add all the forces, all the moments produced by the forces, and that also should be added vectorially with the moment. So we get one resultant moment and one resultant force, and that single resultant force and resultant moment can be represented as an equivalent single resultant force at a particular point where this moment can also be cancelled. Okay. So that is what we do at various problems. So we combine a given couple and a force and produce a single equivalent force, or replace a force or a set of forces or set of moments by a force couple system. Okay, depending upon the application, depending upon the facility that we have for calculation or workout, we choose a different way of perception or different way of solving the problem. Okay, so as shown here in these figures at the right side, we have lot of forces and a moment shown there. So with all these forces at different directions, the couples are found out and the resultant force is found out, and finally in the third figure a single resultant moment and a single resultant force are obtained or represented. Okay, so it is also given at the bottom. Fr or the F resultant is equal to sigma F, and Mr, that O stands for the point about which we consider moment. M resultant about O is equal to sum of all the moments plus sum of all the moment about O. Okay, so we see a small problem through which we see the concept better. So there is a beam. Okay, so in this beam the problem asks us to reduce the system of forces shown to an equivalent force coupled system at A, and then it also asks us an equivalent force coupled system at B, and also as a single resultant force or single force or resultant. So here for the solution we have to compute the resultant forces about A and then convert it by moving it to B and then moving it to appropriate place where the couple can be replaced. So here as we compute, R is equal to sigma F. So R is obtained as shown there. R is equal to minus 600 newtons J. Okay, and moment about A is equal to R cross F. So there is a cross product by which we get moment as minus 1880 Newton meters into K. So here all the forces are vertical or in J direction. Okay, and all the distances are in X or I direction. So here the calculation is very simple. If they are in different directions, we have to use cross product in determinant form to solve it. So here after finding it at A, we move it to B. The force value doesn't change, but there is a moment included based on the distance between A and B. Okay, so from that we obtain moment about B as 1000. So here the answer is minus 600 J along with 1000 Newton meters K. Okay, at B. This is the second part of the problem. So finally for the third part, we move it to the distance where the couple is eliminated. Okay, so we find that from the expression we find that the distance to be moved is 3.13 meters and this value of force doesn't change. Okay, so here we have studied about force coupled system, we have studied about an equivalent system, and we have also solved a problem with which we have understood. So with this we complete the session. Thank you.